Suppose we want to convert the complex number 3 plus 2i to polar form. The first thing we need to do is plot this complex number on an Argand diagram. So the complex number 3 plus 2i has two parts. It has a real part, which is plus 3, and an imaginary part, which is plus 2. So plotting the complex number 3 plus 2i is equivalent to plotting the point 3, 2 in coordinate geometry. So the x, our real value, is plus 3, and the y, our imaginary part, is plus 2. So we go to plus 3 on the real axis, then we go to plus 2 on the imaginary axis, and we have this rectangle formed. So this form of a complex number is often referred to as the rectangular form. Another word that's often used is Cartesian form. The word Cartesian is named after René Descartes, who was involved in developing coordinate geometry. So in general, a complex number in rectangular or Cartesian form would be given by x plus yi. Now an alternative way to specify a complex number is to give its distance to the origin, which is the modulus of the complex number, which is denoted by the letter r, and the angle that it makes measured anti-clockwise from the positive real axis. That angle is usually denoted by the letter theta. So it's measured anti-clockwise from this positive real axis. For this particular complex number, you can see that theta is an angle between 0 and 90 degrees. So if we know both r and theta, we have fully specified our complex number. So how do we relate r and theta to x and y? Well, we just use some trigonometry. You can see that we have a right-angled triangle formed here. The side opposite theta is just the y value, our imaginary part of our complex number. So that's plus 2, and the side adjacent to theta is plus 3. Now I'm just going to look at the lengths of these sides. So even if x and y are negative, we will just consider lengths of these sides, and a length is a magnitude, it's a positive quantity. So we can see what theta is. We can see straight away that the tan of theta is the side opposite theta, which is 2, divided by the side adjacent to theta in this right angled triangle, which is 3. Now what about r? Well, we can use Pythagoras' theorem to find r. We have the two short sides of a right angled triangle, so the square and the hypotenuse is the sum of the squares of the other two sides. So r squared equals 3 squared plus 2 squared, which means that r is the square root of 3 squared plus 2 squared. So that's just Pythagoras' theorem. So you would have seen this in an earlier video. This is known as the modulus of the complex number, and we use vertical lines to denote the modulus of the complex number 3 plus 2i. But we'll usually use the letter r when we're getting polar form. Now let's look at the cos of theta. I want to give the connection between the x value, our real part of this complex number, theta, and the modulus r. Cos of theta is the side adjacent to theta, which is 3, divided by the hypotenuse, which is r. And since r is the square root of 13, we see that cos of theta is 3 over root 13. The sine of theta is the side opposite theta, which is 2, divided by the hypotenuse, which is r, which is we know as root 13. So you can see that we can write the real part of our complex number, which is 3, as r multiplied by the cos of theta. And we can write the imaginary part of our complex number, which is plus 2, as r times the sine of theta. I haven't actually wrote down what theta is in degrees. You could just get inverse tan of 2/3 if you want to do that. You could also, of course, get inverse cos of 3 over 13, root 13, or you could get inverse sine of 2 over root 13. Theta is 33.69 degrees. Now, theta and r are known as the polar coordinates of this point here. So the Cartesian coordinates would be 3, 2. The Cartesian or rectangular coordinates, but the polar coordinates would be r comma theta. So r is root 13, theta is 33.69 degrees. Of course, we won't normally write polar coordinates like this. What we will do is write our complex number in the form r times cos theta. So that's what this is here, which is root 13 cos of theta, which is 33.69 degrees, plus I times, or well, we could put the I after, but often I is written in front here, times r sine theta, sine of 33.69 degrees. Okay, so if you multiply root 13 by the cos of 33.69, you'll get 3. And root 13 by the sine of 33.69 will give you 2. So it just comes out of basic trigonometry. The root 13 is often factorized out. Root 13 is r. So we have cos theta plus I times sine theta inside brackets. So in general, this x here, which was 3 in this problem, is actually r multiplied by cos of theta. So we multiply the modulus by the cos of the angle that is measured anti-clockwise from the positive real axis. And the imaginary part of our complex number is given by r times sine of theta. And it doesn't matter what theta is, it turns out. It's fairly clear here when theta is an acute angle, that is an angle between 0 and 90 degrees. But if theta is an obtuse angle or a reflex angle, these relationships will still hold. These relationships follow from trigonometry, not just for acute angles, but for angles where we need to consider a unit circle, where cos theta, sine theta are the coordinates of a point on a unit circle. So this comes from trigonometry. And there are times when cos theta and sine theta are negative. They're going to be positive in this quadrant, but they will be negative in other quadrants. So the complex number x plus yi can be written as r cos theta plus r sine theta times I, and we can factorize out r, so we get r into cos theta plus I sine theta. The I is often written before the sine theta, probably just to avoid confusion, because if you write I after sine theta, it looks like we're getting the sine of theta times I. Of course, we're not getting, I is not part of the argument of this sine function, so that's probably why it's written out here. So this form of a complex number is known as the polar form of a complex number. Now the reason why we write a complex number in polar form is because it's much easier to do calculations with complex numbers in this form. Okay, so I'll explain more about that in later videos. Now, suppose we want to convert minus 1i to polar form. The first thing we need to do is plot this complex number on an argand diagram. The real part of this number is minus 1, so x is minus 1. The imaginary part is the coefficient of I, which is minus 1. So we go to minus 1 on the real axis, which is here. Then we go to minus 1 on the imaginary axis. This point here actually represents the complex number minus I, or minus 1i. But I leave out these units. All the values here are understood to be in units of I. So I'll just write minus 1, meaning minus 1i. So here it is. What we need are its distance to the origin, which is its modulus, and we need theta. So we need r, which is the modulus, and theta, which is measured anti-clockwise from the positive real axis. So this is the positive real axis. So we measure anti-clockwise this way. So we see that theta is an angle between 180 degrees and 270 degrees. All you need to know to convert a complex number from rectangular to polar form is this relation here. So we need r and theta. To get r, we just get the modulus of the complex number, which is written like this usually, just these vertical lines, and this is just Pythagoras' theorem. So we have a right angle triangle formed here, so we have lengths of 1 and 1. So we have the square root of 1 squared plus 1 squared. So the two short sides are 1 each. So this leads us to the square root of 2. To get theta, we could start by getting this angle A. This angle A is an acute angle in this right angle triangle here. We note that the tan of A is the side opposite A in this right angle triangle, which is 1. Forget the coordinates at this point, we're just looking at lengths of sides of a triangle, so the lengths are positive. So the tan of A is opposite over adjacent, 1 over 1, which is 1. So that means that angle A is the inverse tan of 1, which is 45 degrees. Now you could write this in radians if you like. We just remember that pi radians is 180 degrees. We don't write in radians here. So the units here are understood to be radians. So if pi radians is 180 degrees, then 45 degrees is a quarter of 180. So 45 degrees is a quarter pi, or pi over 4 radians. So what now is theta? Well, to get theta, we just add 180 onto 45 degrees. So that's 225 degrees. Now what's that in radians? Well, how many 45 degrees angles fit into 225 degrees? Well, 4 of them make 180, and a fifth one makes 225, so that's 5 pi over 4. So having found what r and theta are, I'll leave theta in degrees, we can write down the complex number minus 1 minus I in polar form. So r goes out here, and inside the brackets we have cos theta plus I sine theta, where theta is 225. Now you can check this on your calculator. If you get the cos of 225 and multiply by the square root of 2, you should get minus 1. And if we get the sine of 225 and multiply by the square root of 2, which is 2 to the power of a half, we should also get minus 1, because the imaginary part of our complex number is minus 1. So it does check out. Suppose we want to convert I to polar form. So we plot the complex number I on the Argand diagram. So here it is. By the way, a complex number and an imaginary, well, the terms complex number and imaginary number are the same, really. I could say this is an imaginary number or a complex number. Okay, now we want r, which is the distance of the complex number to the origin. So r is this distance here. So we don't have to use Pythagoras' theorem. We can just count the units. It's just 1 unit. So r is equal to 1. What's theta? Well, theta is the angle measured anti-clockwise from the positive real axis to a line joining the complex number to the origin. So you can see here that theta is 90 degrees. So now we can write our complex number I, which you can also think of as 0 plus 1i. Real part is 0. This point here is like in coordinate geometry is the point with coordinate 0, 1. We can write it as r, which is 1, times cos of theta, which is 90 degrees, plus I sine of theta. And if you check in your calculator, you'll see that the cos of 90 degrees is actually 0. The sine of 90 degrees is 1. So it all comes down to trigonometry. Now suppose we want to convert the complex number 3 to polar form. Now you might wonder why this is referred to as a complex number, but in earlier videos I said that all real numbers are complex numbers. All the real numbers form a subset of complex numbers. We can think of the complex number 3 as 3 plus 0i. So where does that appear? Well, that appears just on the real axis when we plot it. It's like plotting the point 3, 0. So what is r and theta for 3 plus 0i? Well, r is the distance of 3 to the origin. So you can see that r is equal to 3. We don't have to use any Pythagoras here. Now what is theta? Well, theta is an angle measured anti-clockwise from the positive real axis to this line here. And that angle is 0, because this line lies on the positive real axis. So now we can write down the number 3 in polar form, or 3 plus 0i is 3 into cos 0 plus I times sine of 0. The cos of 0 is 1, so we get 3 times 1 is 3. The sine of 0 is 0, so we just end up with 3. Now let's look at the complex number minus 2i. Well, the real part of this complex number is 0. The imaginary part is minus 2, so we go to minus 2 on the imaginary axis. So this is point is the complex number 0 minus 2i. So we need r, which is the distance of the complex number to the origin, which is this distance here. And you can see clearly that r is 2. R is always positive. And we need theta, which is measured anti-clockwise from the positive real axis. So theta is 270 degrees. Or if you want that in radians, it's 3 times 90 degrees, where 90 is pi over 2, so it's 3 pi over 2. Or if you like, it's 1.5 times 180 degrees, so it's 1.5 times pi radians. So we can write minus 2i, which is 0 minus 2i, as 2 times cos of 270 degrees plus I sine of 270 degrees. And if you want to check that, if you multiply 2 by the cos of 270 degrees, you should get 0. Actually, the cos of 270 is 0. If you multiply 2 by the sine of 270 degrees, you will get minus 2.